There are 20 billion Earth-like planets in our galaxy. We've confirmed 45 candidates. Of the remaining 20 billion, we know almost nothing. Not whether they have atmospheres, not whether they have water, not whether any of them could sustain life. That is about to change. ESA's PLATO telescope is launching later this year. It carries 26 cameras, will monitor 245,000 stars simultaneously, and is designed to do one thing that no telescope before it has done at scale: find Earth-sized planets around Sun-like stars and measure them well enough to say whether they could actually support life. This is the mission that could answer one of the oldest questions in science. The way we find planets from space is by watching stars blink. When a planet passes in front of its star, a transit, the star dims very slightly. For an Earth-sized planet around a Sun-sized star, that dimming is about 0.008%. To detect it, you need to measure a star's brightness with extraordinary precision, continuously, over months or years. This is the transit method, and it's already produced results. The Kepler Space Telescope used it to confirm thousands of exoplanets. TESS followed with thousands more. But both of those missions had a fundamental limitation. Most of the stars they observed were too faint, too far away, or too poorly understood for scientists to characterize the planets they found in detail. Knowing a planet exists is not the same as knowing what it is. PLATO was designed to close that gap. Its target list focuses on bright, nearby stars. Stars close enough that follow-up observations from ground-based telescopes are actually possible. When PLATO detects a planet, astronomers can point other instruments at the same star, measure the planet's mass, study its density, model its interior, and eventually, with the right equipment, analyze its atmosphere. That chain of observations, from detection to characterization, is the path to knowing whether a world is truly Earth-like. Not just Earth-sized, not just at the right distance from its star, actually Earth-like. Rocky surface, liquid water, the conditions that life as we know it requires. The 26 cameras are the engineering solution to this problem. Most space telescopes have a single primary mirror. PLATO has 24 cameras arranged in 4 overlapping groups, giving it both extraordinary light-gathering power and a field of view covering roughly 2,250 square degrees of sky, about 10,000 full moons. It can watch a vast swath of stars at once, at the precision required to catch a planet as small as ours. There is a number at the heart of this mission that matters more than the camera count. That number is the orbital period. For a planet to be in the habitable zone of a sun-like star, the region where liquid water can exist on the surface, its year must be roughly similar to ours. Around a star like the Sun, the habitable zone produces orbital periods of several hundred days. To confirm a transit, you need to see it repeat at least twice, preferably 3 times. That means observing the same patch of sky for at least 2 years. Kepler didn't have enough time. TESS observes in 27-day segments, which makes it excellent for short-period planets close to their stars, but nearly blind to the habitable zone around Sun-like stars. PLATO will observe each of its primary fields for 2 to 3 years continuously. It is the first telescope designed specifically to find Earth analogs, not Earth-sized planets in general, but Earth-sized planets in Earth-like orbits around Sun-like stars, detected and measured precisely enough to be worth following up. What makes this different from previous searches is the quality of the target. Every exoplanet mission before Plato has been a census. Count as many planets as possible, map their sizes and distances, build statistical models of what the galaxy looks like. That work has been transformative. It told us that planets are common, that small rocky worlds outnumber gas giants, that multi-planet systems are the rule rather than the exception. But a census doesn't tell you what the planets are made of. It doesn't tell you about the air above them or the water on them. For that, you need stars you can study in detail, planets you can weigh and measure, data you can hand to the next generation of instruments. Plato is designed to create that handoff. The James Webb Space Telescope, launched in 2021, can analyze the atmospheres of exoplanets, but only if those planets are bright enough, close enough, and well enough characterized to be worth pointing at. Plato will find the candidates. Webb and whatever comes after it will do the follow-up. This is the first step of a pipeline that ends with the answer. The question being asked here is the most profound one in science. Not just, are there other Earth-like planets? That answer is almost certainly yes. 20 billion candidates in our galaxy alone suggests that rocky worlds in habitable zones are not a fluke. The real question is, what do they look like up close? Do they have atmospheres? Do those atmospheres contain oxygen, methane, water vapor, the signatures of chemistry that on Earth is inseparable from life? Do any of them show signals that require a biological explanation? We don't have the data to answer that yet. Every confirmed exoplanet in the habitable zone so far is either too poorly characterized to study or orbiting a star so different from our own Sun that the comparison to Earth breaks down. Plato changes the sample. For the first time, we will have a catalog of Earth-sized planets in Earth-like orbits around Sun-like stars, measured precisely enough to matter. What we find when we look at those planets, really look, with every instrument we have, may be the most important discovery in human history, or it may deepen the silence. Either answer tells us something, but we have to look first.